Welcome back, relativity students. This presentation will be solely dedicated to looking at one interesting problem, which seems to present, at first glance, a paradox of sorts. But you'll see that it's not really a paradox at all. It just seems that way because you're a relativity noob, but we'll fix that. So let's start by reviewing two of the conceptual results from special relativity. There's the length contraction. Capital L is the length of something that's moving in the lab frame S. And script L would be the length of that same object in the reference frame of the object. So if you were, let's pick something concrete like an airplane flying through the air, L could be the length of the airplane as measured by somebody on the ground. Script L could be the length of the same airplane measured by somebody in the airplane and moving with it. So really the proper length, as we call it, has to be measured in a reference frame where both endpoints of the object are at rest in that reference frame. Obviously, if you're watching the plane move over the ground, then in the reference frame of the ground, the endpoints of the airplane are moving. So a measurement of the distance between those endpoints would not be considered the proper length. Gamma is that factor 1 over the square root of 1 minus beta squared, where beta is your light speed. That's your speed compared to the speed of light, that ratio. The other effect that's commonly discussed is time dilation. Delta tau is what we call the proper time. That's the time between two events in an inertial reference frame in which those two events happen at the same position. And delta t would be the time interval measured by somebody in another reference frame in which those two events do not happen at the same position. Okay, and we're really not going to use this much in this presentation, but we certainly will be looking or thinking about this one. So here's the problem. It involves a baker or a chef. Yeah, I guess a baker because we're talking about desserts here. Here's a big sheet of cookie dough, and it's on a giant conveyor belt that's going to be moving this dough to the right, I believe. And I wanted a picture with a smaller, like a narrower piece of dough, but I couldn't find one. So here it is, giant piece of cookie dough. And the baker has a star-shaped cookie cutter. And here's what's going to happen. In the reference frame of the baker, he or she will turn on the conveyor belt. And so the dough is being rolled to the right. And the baker is just going to plop that cookie cutter down repeatedly, plunk, 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 as the dough goes by to cut out the cookies. And they will end up with the sequence of these star-shaped cutouts before they go into the oven for baking. So the cutout has the same shape as the cookie cutter. Seems fairly obvious. And this is important. Try to imagine that the dough is etched at regular intervals. Maybe it's got some kind of crease. That the length of the interval is not important, but you'll need that in order to picture this the seeming paradox that we're about to encounter. And I don't know why some of these creases are red and some are black. Just ignore that. Okay, what have I done here? Why would the picture go from here to here? Well, this is what the etched dough would look like at rest in the baker's frame of reference. We could call that frame S. But as soon as you get the dough moving, we know that it will be length contracted, or you could even say Lorentz contracted. So all distances in the direction of motion are contracted. Remember that distances transverse to the direction of motion are unaffected. So the sheet of dough won't be any narrower, it'll just be shorter. Like if it was a 20-foot sheet of dough, now it's less, maybe 15 feet. Okay, and here gamma is in the denominator. Remember that gamma gets bigger the faster you go. In fact, as you approach the speed of light, gamma explodes asymptotically. It goes up to infinity as you approach the speed of light. So if you were going 99.99% the speed of light, gamma would be an extraordinarily large number, in which case the length of the dough would be divided down by an extraordinary factor. So again, if the dough is going 99.9% the speed of light, then instead of being a 20-foot sheet of dough, it could be a 1-inch sheet of dough, which is ridiculous to even imagine. Let's consider a much more modest speed, because otherwise the picture would be too compressed here. Okay, so the effect of this is, and I tried to choose the size of the cookie cutter so that it's just a little bit wider than one of these subdivisions or regular increments on the dough. See how from point to point, it's just a little bit wider. And if the dough were not in motion, and so it were not length contracted, that star-shaped cookie cutter would probably be less wide than one of these divisions. Let me go back here. See that? Unfortunately, I don't have the cookie cutter on this particular slide, but I think from point to point, it would have a width a little bit less than one of the divisions. But when the dough is contracted, then each of these cutouts is a little bit wider than one division. Okay, so what happens after the baker is finished punching out all these cookies and he turns off the conveyor belt and it comes to rest? What's going to happen to the dough? Well, it's going to stretch back to its original length in the lab frame. And that includes the cutout of the cookies. So it's going to end up looking something like this. So if we analyze what happens in the frame of reference, or the inertial frame of the baker, we're forced to conclude that when the conveyor belt is turned off, these cookies are going to look stretched out laterally. They'll be distorted in this manner. That's the conclusion that the baker must come to. Now let's turn around and analyze this same situation in a different reference frame. We'll put ourselves in the inertial frame of the dough. So as if we're moving with the dough. And if we're moving with the dough, then since the dough is moving to the right in the baker's frame, then from the dough's perspective, the cookie cutter would actually be moving to the left as it is being plopped down to cut out the cookies. Okay, so we're in, you could call this frame S prime, the dough's frame of reference, and you'll notice that the divisions are no longer Lorentz contracted. The cookie cutter itself would be Lorentz contracted. And so you might think that when you bring that cookie cutter down repeatedly to punch out the cookies, you'll get something like this. And check it out. Now, more than one star fits into each division, almost 2 stars per division. So that when the dough is brought to rest, or I guess from the dough's perspective, you would say when the cookie cutter is brought to rest, basically when the baker turns off the conveyor belt and everything stretches back out, you'd end up with this. Have I done this correctly? Yeah, I guess I didn't even need to say that, because we don't need to think about the cookie cutter being restored to its original length. All we care about is what the dough looks like, and we're already in the dough's frame of reference. So we've already reached the important conclusion here that almost 2 cookies fit in each division. What is going on here? Because that is definitely contradictory to the conclusion that we reached when we analyzed this cookie cutting from the baker's frame of reference. So which is it? Less than 1 cookie fits into each division, or almost 2? Because they can't both be true. Both observers would have to agree on the final result. Once the conveyor belt is turned off, yes, when the belt is in motion, then the dough and the baker are in different inertial frames. So they're going to observe different things. But once the dough is brought to rest, then the reference frame of the dough and the reference frame of the baker are the same. They've got to agree on the final outcome. So it really does appear that we're presented with a paradox here. One of the 3 major results from special relativity, those 3 being length contraction, time dilation, and the relativity of simultaneity, one of those, in this case, length contraction, seems to be leading us to a contradiction. which would lead one to suspect that consideration of one of those other two, or perhaps both results, aside from length contraction, will rescue us from the conundrum. So maybe we just don't get what's going on here because we haven't considered the other effects. Okay, to that end, let's take a closer look at the relativity of simultaneity. Here's a reference frame fixed to the ground. I'll call this reference frame S. And we've got some regular tick marks along the x-axis. So every position on this screen has a particular x coordinate, and we could look at the difference between two x coordinates and talk about the displacement. Here's a high-speed train moving to the right in frame S. And let's say it's the California high-speed rail finally, which means we must be in the year 2500. Actually, I prepared these slides before the pandemic. So we've got, this whole project's probably been pushed back another 200 years. So let's call this the year 2700. And we'll have to fix a set of axes to the train. So we have an inertial reference frame moving with the train. We'll call that frame S prime, with axes x prime, y prime, etc. V is the speed of the train over the ground. You've seen this before. And now let's talk about units. I'm going to do something that was not done in your book. It seems challenging at first, and unnecessary, but you'll see the advantage in a moment. I'm going to choose a simpler system of units. So in the imperial system of units, the speed of light is 186,000 miles every second. Those are not SI units. Let's do this. Some of you may know that when you're looking at the sun, you're actually looking 8 minutes into the past. It takes the light 8 minutes to go from the center of the sun to the center of the earth, or surface to surface. I don't know. This isn't to scale anyway. This is the distance, or I should say this distance is much greater than either of the radii. Okay, so when you talk about how far away the sun is, rather than saying 1 astronomical unit, which is actually pretty convenient, or 150 million kilometers, you could just say it's 8 minutes. In fact, I think if you took any random person with some basic science knowledge and asked them, what does it mean to say that the sun is 8 minutes away? Well, they're probably going to realize it doesn't mean you can drive there in 8 minutes because it's much farther away than that. It doesn't mean you can take a boat or a plane. What the heck could get from the sun to here in 8 minutes? Well, that must be how quickly light gets to us. So it's really the distance that light travels in 8 minutes. So what we're doing here is using a unit of time to actually describe a distance. And the connection there is the speed of light. So we can use units of time as units of distance if we allow the speed of light to bridge the two. So let's just do that with the SI unit of distance, 1 meter. Now, 1 meter is about 3 feet. That's a really short distance as far as light is concerned. It takes a very insignificant amount of time for light to go from here to here. In fact, 1/300 millionth of a second. That's an inconvenient number, 1/300 millionth of a second. Let's just call it a meter of time. How far does light travel in 1 meter of time? 1 meter of distance. Well, that's not a very long time, is it? It doesn't take light long at all to travel 1 meter. So a meter of time is a very small unit of time. And that's not really important to the rest of the discussion. What is important is that we're using the same units to measure time and distance. Okay, now, did I actually put up a slide for this? Yes, I did. So you could say that light travels 186,000 miles every second, or make things simpler, make things easier on yourself and just say light travels 1 meter of distance every meter of time. And then not only do the ones cancel, so to speak, but the units do as well. I shouldn't say the ones cancel, it's just that the ratio is 1. It's not like 186,000 over 1, it's just 1 over 1. Okay, so the speed of light in this cool system of units is just 1 with no units at all. And now you're already probably thinking, well, that's convenient because that means the speed of something slower than light, like a train or an airplane or a car is going to be some number between 0 and 1. What we're really talking about is light speed, your speed compared to the speed of light. Okay. So we haven't looked at this in any detail, but here are the so-called Lorentz transformation equations. If you have recorded the position and time of any event in the train's frame of reference, that high-speed rail we were looking at, that's in the S prime frame, you can use these transformation equations to find the corresponding time and position as measured by somebody in the ground frame of reference, or ground inertial frame S. That's what these transformations allow you to do. And the most general type of transformation would give you X, Y, Z, and T in terms of X prime, Y prime, Z prime, and T prime. We're looking at the special case where the X axes are sliding parallel to each other. The train's moving to the right along the X axis. You could also look at a situation where you've got a rocket ship moving kind of in between the X and Y axes, and then the Lorentz transformation equations would be a little more complicated. Okay, well, these are cumbersome, especially this half of it, because there's just too many C's running around. It's not very nice to look at. And that's deceptive, because it should be nice to look at. It should be very nice and aesthetic and simple. So if we use this system of units, what happens to all these pesky C's? Vanish, be gone, poof. If you get rid of those, you're left with this. Much nicer to look at. In fact, they look almost exactly like the Galilean transformation equations, which are described in your book. The only difference is this factor of gamma out front. So if you're going to use this form of the equations, at first glance, you recognize there's no factors of C running around. That must tell you that you're using this system of units where you measure time and distance in the same unit, the meter, for instance. And so it's understood that the speed here is really a number between 0 and 1. In a prior presentation, I would have called this beta. I would have used the letter beta. So this really is beta. It's your speed compared to the speed of light. So it's a number between 0 and 1. And gamma, of course, is 1 over the square root of 1 minus beta squared here, 1 minus v squared. This is your speed as a number between 0 and 1. Okay, now, very often, it's much more useful to use these in their differential form. I suppose that's how you would say it. It really just means take two events, like two firecrackers going off in the train. Each of those exploding firecrackers has a position and a time. So you could look at the distance between those two events in the train's frame of reference. That would be a delta x prime, and the time between them as well, that would be a delta t prime. So really just evaluate this for event 2, evaluate this for event 2, then do the same thing for event 1 and take the difference, and you would end up with this. For those of you who are a little more calculus savvy, you could just take the differential of both equations and you would have dx, dx prime, dt prime, but really dx's and dt's are actual delta x's and delta t's. They're just infinitesimal. So I'm going with the non-infinitesimal notation here. Okay, so this is a time interval as measured in the S prime frame, and this is a distance between two events as measured in the S prime frame. Here are the corresponding quantities in the ground frame. And I'll just mention in passing, there's this magical quantity called the space-time interval. I really should have put the word space-time here. So we've talked about the fact that delta t changes as you go from one reference frame to another. That's time dilation. The person in the train might age by 10 years. Well, that's a little too much. Let's say 10 hours, whereas the person on the ground might age by 12 hours. So time is relative and length is also relative. That's the business with the length contraction. But the one thing that's not, quote, relative is this magical quantity, the space-time interval. So if you take the distance between two events, square that, take the time between the two events, square that, and then subtract those two quantities, you're going to get a number that will be the same for all observers. How cool is that? Totally not common sense, not intuitive at all. Nobody had any clue that that was the case prior to 1905. Why would you? Okay, let's imagine two early 2000s cell phones here. They're not even flip phones, are they? And as seen by somebody on the train, let's suppose that these cell phones ring simultaneously. They both receive a call at the same time, maybe from the same telemarketer. If those events are simultaneous in the train, then the time difference between the two events would be zero. So their time coordinates could be T2 prime and T1 prime. T2 prime could be the time at which phone number 2 rings, and T1 prime would be the time at which phone 1 rings. And we're looking at the difference between those two times. If they're simultaneous in the train, then delta T prime would have to be 0. Okay, so we take that and we plug it into the Lorentz transformation equations, which I did not derive in this video, right? And let's focus on what happens to the bottom one. So if this is 0, then we only have to worry about this second term. What does this equation say? It says that if there's any distance at all between those two cell phones in the train, in other words, if delta x prime is not 0, then neither is delta t. Well, delta t is the time that passes between the two events as seen by somebody in the ground frame. So evidently, if these two cell phones are in different locations in the train, then there's no time at all between the two events. Oh, I misspoke. If they're in different locations, there is a non-zero time interval between the two. That is to say, they're not simultaneous. Whoa. So you can see the relativity of simultaneity right here in the Lorentz transformation equations. They may be simultaneous in the train, delta t prime is 0, but delta t, the time interval between those events as measured in the ground frame, is not 0 by virtue of the fact that they're in different locations. So if these two cell phones had rung simultaneously at the same position on the train, then they would still be simultaneous for somebody on the ground, but not if they're in different positions. What a trip. Now it's time to take a look at space-time diagrams. This is probably your first look at a space-time diagram. It's a lot like those motion diagrams that you first learned to interpret when you took calculus-based mechanics a couple semesters ago. And this is equally challenging. There's a little twist here. You're probably used to plotting position, oops, laser pointer, position vertically versus time horizontally. But in almost all books on relativity, the custom is to do the opposite. The vertical axis is time. And we're not going to break tradition here. So you'll just have to get used to it. And let's talk now about the world line of something moving through space-time. We'll take a cow, for instance, a cow that's just chilling at a particular position on the x-axis. It's not walking left, it's not walking right. It's at rest in the lab frame. So that means its x-coordinate is not changing in time. And so the cow's world line would look like this on a space-time diagram. At t equals 0, when we start the clock, the cow is, let's say, right here on the x-axis. A moment later, time has advanced, right? We're going this direction as time goes forward, but the cow has not moved right or left. It's at its same position. So the cow's world line just looks like a vertical trajectory on the space-time diagram. Now, again, if this were mechanics and we were plotting position vertically versus time, then this line would actually be horizontal, and you would immediately recognize that the slope of that line is 0, which tells you that the cow is not moving. Its velocity is 0. So we can tell a similar thing here. Its vertical slope, so to speak, is 0, so we know that the cow is not moving. What happens if the cow is walking slowly towards the origin? Well, its x-coordinate is decreasing, and we can see that here. Very gradually, as time advances, the cow is moving back towards the origin right here. So the negative velocity is visible in the fact that the line is tilted to the left just a little bit. If the cow was walking to the right, then this line would be tilted the other way. So what about the train, which obviously goes faster than the cow, or at least it's supposed to? Okay, why do I have the two cell phones back on here again? Okay, let's look at the world line of the train itself. In fact, specifically, let's look at the world line of the origin of the S prime inertial reference frame or inertial frame. So there's a particular place in the train that falls on the origin of that coordinate system. Let's look at the movement of that part of the train through space-time on a graph of x versus t. So I should have pointed out, this is really the space-time diagram in the reference frame of S, or in the S reference frame. Okay, so the fact that the origin of the train was at x equals 0 at the time t equals 0 means that when the clock was started, this point right here was just passing through the origin of our S reference frame or inertial frame. So sometime later, the origin's over here. But at t equals 0, these two origins coincided. And you can see that the train is moving to the right because the space-time, or the world line, as it's often called in relativity, is tilted to the right. And you'll notice that it's tilted more than the other line that I drew. See how this one's barely tilted? That's because cows don't move very fast, usually, and trains are supposed to move much faster. But you'll notice that the world line is not tilted this much. Here's a line that makes an angle of 45 degrees with the t and the x axes. And if we're using the system of units where we measure time and distance in the same unit, the meter, what could possibly travel 4 meters of distance in 4 meters of time, which is the same as saying 1 meter of distance every 1 meter of time? There's only one thing that goes that fast. Actually, that's not true. I was going to say light, but we know that gravitational waves also travel at the speed of light, and they're not light. So, okay, there's only a few things that we know of that travel at the speed of light. So you'll never see the world line of a massive object. Massive meaning it has mass. It doesn't have to mean it's really massive, you know. It could be a marble or an electron. That world line will never be tilted over this far, because if it were, that would imply that the object was going at light speed, which is not possible in the theory of special relativity. Okay, what about this bunny here, which is hanging out at the origin? If the bunny never moves, then its x coordinate is always 0 for all time. So I've drawn the bunny's location on the space-time diagram at subsequent time intervals. You could just connect all the dots, and that would be the world line of the bunny. Okay, and you'll notice that that world line coincides with the t-axis, which is a really important point. If you look at the world line of something stationary at the origin, that world line coincides with the t-axis. So put another way, the t-axis is the world line of something stationary at the origin. It's the same thing. And we're going to take that logic and apply it in the reference frame of the train, S prime. The t-axis is the world line of the unprimed origin. Okay. So what about the world line of the primed origin? That's the origin of the S prime frame. Well, we just looked at that, right? That was the line that's tilted over. Well, that must be the t prime axis, right? If the world line of the origin of the S frame is the t axis, then the world line of the origin of the S prime frame must be the t prime axis. Seems simple enough. So that's how you find the t prime axis. We're going to be plotting the t prime and x prime axes on the xt space-time diagram. And what does every point on the t prime axis have in common? Every one of these points has an x prime coordinate of 0, not an x coordinate of 0, because look at the picture. If you watch the motion of the origin here, the origin of S prime, its X coordinate, that's as measured in this reference frame, is always increasing, but its X prime coordinate is always 0, right? Because it's moving with the train. So every point on this world line has an X prime coordinate of 0. Okay. Here are the clean versions of the Lorentz transformation equations. Let's examine the relation between the X and T coordinates of all the points on the world line of the train's origin. We've just established that the origin always has an X prime coordinate of 0, and that makes these equations a little bit simpler. The top one is just gamma v t prime. The bottom is gamma t prime. Yeah, that's it. And then what we can do is divide the top equation by the bottom equation. So when we divide the left sides, we get x over t. And then you take gamma v t prime and divide it by gamma t prime. You'll notice that the t primes cancel. And so do the gammas. Okay. And we end up with this, which is something you've known since grade school, right? The coordinate of the train's origin is just speed times time. This is just distance equals speed times time. Again, we're looking at the coordinates in the ground frame. Okay, so this is really the equation of the t prime axis. And you can tell by looking at it that this is a line that goes through the origin, right? Remember y equals mx plus b, where b is the intercept. This equation has no intercept, or it has an intercept of 0. So we know that this is a line that goes through the origin. And just now I mentioned y equals mx plus b. What's the m in mx plus b? Well, here it would be this number. It's the coefficient in front of your horizontal or your other variable here. So that's got to be the slope. But remember, we've flipped the usual roles of the axes. So if I go back to the equation here, do I have it? Yeah, this is our horizontal coordinate, and this is our vertical coordinate. So think back to algebra. Instead of y equals slope times x, it's kind of like x equals slope times y, but I'm using the letter x in 2 senses here. So that's going to confuse you. Just think of it this way: because we're switching the roles of the variables from their normal usage, then we're really measuring the slope from the vertical axis. So that's got a really nice interpretation. The slope of the t prime axis tells you directly the speed of the origin of that S prime frame, the speed of the train in this case. Of course, that only works if you're measuring speed between, or as a number between 0 and 1, light speed. Now, this next fact is not so obvious. In fact, off the top of my head, I don't even recall how to show this, but at least the symmetry makes sense. If the t prime axis is tilted by this much from the t axis, then the x prime axis is tilted by the same amount from the x axis. So what's the meaning of the x prime axis? Well, just ask yourself about the meaning of the x axis. Any event that happens on this axis happens at what time? All these events on the x axis have what in common? They occur at time t equals 0, right? Time increases in this direction. So the x-axis is the set of all events that happen at time t equals 0 in the S frame. And that must mean that the x prime axis is the set of all events, space-time events, that happen at time t prime equals 0 in the S prime frame. That's the meaning of the x prime axis. Okay, so now what I've done is draw lines of simultaneity in the lab frame, the ground frame. So any event falling on this line happened at this particular time. All of these events were simultaneous at some later time. All of these events were simultaneous at some later time. So these horizontal lines, equally spaced, are lines of simultaneous events, or lines of simultaneity. For instance, suppose, as seen by somebody on the ground, these 5 cell phones all rang at the same time. In fact, at the particular time, 2 meters. So instead of measuring time or reckoning time, that sounds cooler, in seconds or hours. We're reckoning time in meters. And you'll recall that a meter of time is a very short time because light takes a very insignificant amount of time to travel a distance of 1 meter. So 1 meter of time is a very short unit of time. Okay, so if they all ring at 2 meters, and notice that they're equally spaced on the x-axis, this is what that would look like on the space-time diagram. This dot represents the first event of the leftmost cell phone ringing at time 2. This is the next cell phone over ringing at the same time. Okay, so all 5 cell phones ring at the same time in the S frame. You can see that because they fall on a horizontal line, which is a line of simultaneity in the ground frame. What's the significance of lines which are perpendicular to the lines of simultaneity? Well, every point on this line has the same position. So these would all be a bunch of events that happen at the same x coordinate, the same location in the ground frame. I don't have a cool phrase for that. We've got lines of simultaneity and lines of equal position, I suppose you could say. And we've already looked at an example, right? The cow that's just hanging out at 6 meters. It never moves its position. So as time advances, we could sample the cow's location at equal times, and we find it's always at the same position. So a vertical line is the world line of something stationary in the S frame. Okay, and now we're prepared to overlay on top of that grid the x prime and t prime axes. And now our task is to figure out what lines of simultaneity and equal position look like for the S prime frame. Well, how did I come to this conclusion? Let me back up. All of these lines of simultaneity are parallel to each other, and this is important, parallel to the x-axis. That's worth repeating. In the space-time diagram for frame S, lines of simultaneity are parallel to each other and especially to the x-axis. So for the S prime frame, lines of simultaneity appropriate for the S prime frame must be parallel to one another and to the X prime axis. So all I had to do was draw a bunch of lines which are parallel to the X prime axis. And I spaced them equally as well, so that we're marking off equal intervals of time in the T prime, excuse me, in the S prime frame. So this event right here happens later than this event. This event happens later than this event. This event happens later than this event. And these are equal time intervals as measured by somebody in S prime. And one of the surprising features of relativity is really visible right here in the graph. It's actually easier to interpret looking at this graph than it is thinking about the Lorentz transformations. All of these events are simultaneous according to an observer in the train, but they are clearly not simultaneous as measured by somebody on the ground because they're cutting across the horizontal lines of simultaneity. See that? So I think I have a better slide actually. Every event on this line is simultaneous in the train frame, not the ground frame. Back to this example. Yes, all of these events, these various cell phones going off at time 2 meters in the ground frame, they would fall on this line of simultaneity. This is the t equals 2 meters, that's 2 meters of time, line of simultaneity in S. But look at how this line of simultaneity cuts across several different lines of simultaneity for the S prime system. In fact, we can assign actual times to these lines. Remember, the X prime axis is the set of all world events, or the set of all events, I should say, that occur at time t prime equals 0. So that's when the clock starts in the S prime frame. And so this line of simultaneity must be 1 second later in S prime. Every event on this line of simultaneity occurred at time 1 meter, I should say, 1 meter, not 1 second, in S prime. all of these events occurred at time 2 meters. That's 2 meters in the S prime frame, not 2 meters in the ground frame. Okay, so the fact that these lines of simultaneity are skewed or tilted with respect to the ones from the other reference frame tells us that time is relative, or I should say that simultaneity is relative. Here are the events corresponding to the phones ringing. I think there were 5 phones, only 4 of them fit on the screen here. So they may be simultaneous for a ground observer, but they're clearly not simultaneous for somebody on the train. In fact, we can see the order of the events. Check it out. This cell phone is the one that rings first, as seen by somebody. Oh, when I say seen, I really mean observed by somebody on the train, because it is on the T prime equals 0 line of simultaneity. And then this cell phone goes off at time 1 meter, as measured by somebody on the train. This cell phone goes off at time 2 meters. So it's very clear that the cell phone rings are not simultaneous. Beyond being able to see that easily from the diagram, we can also see the spatial relation. It's the ones further to the right that happen first. So the farther you go to the right, the earlier in time those events happen, as seen by somebody on the train. And that's really the general relationship I'm hoping you can take away from this presentation here. We're not really doing any calculations here. We're just looking at the way the order of events depends on the relative motion of the 2 reference frames and the position of those events. And here's an example that I like to use, a little picture in my head that helps me remember this relationship. Here's a set of firecrackers or fireworks that are all exploding simultaneously in the ground frame. Imagine they've all been launched together and they all explode at the same time. Are they going to look simultaneous to somebody in the train? Well, we've just established that simultaneity is relative. So for the train moving to the right over the ground, we know that any set of events like the fireworks, which are simultaneous in the ground frame, will no longer be simultaneous in the train frame. And the ones farther to the right actually happen first. So the farther you go to the right, the earlier in time those events will happen. And that means that somebody on the train would observe this firecracker going off first, and then this one, and then this one, etc. I say observe because we can't necessarily conclude that that's the order in which they would see the fireworks go off, because there's still the added complication of the fact that it takes time for the light to travel from the source to the eyeball of somebody on the train. So that would require some further thought. So when we say, they see the one on the right go off first, again, that's shorthand for really they would observe, which is also shorthand for saying if you had a whole bunch of trained laboratory assistants positioned throughout this reference frame, writing down the times and positions of all the various events, and then you assembled the data later and looked at which ones happened first and where, then you would be able to establish this result. But that's pretty cool, right? To imagine all of those fireworks going off in a different order, or subsequently rather than simultaneously. So hopefully, after spending a little time thinking about that, you can figure out how to resolve this so-called paradox, which is not really a paradox at all, because when we first analyzed this from the baker's perspective and then from the point of view of the dough, if cookie dough can have a point of view, I mean the reference frame of the dough, we only used one result from special relativity, and that was length contraction. We ignored the relativity of simultaneity, which is why we ran into problems. So let's include that now in our analysis. And let's see here. I think the arrow on the dough indicates that the dough is moving. So right now we're in the baker's frame, which is basically the cookie cutter's frame of reference. So the dough is zipping past to the right. And to help you picture this, imagine you're looking at the cookie cutter from the side. I suppose it would look kind of like this if you really were looking at it directly from the edge. And so it's not a great picture. I'd have to flip the dough around as well. But so you're at like eye level with the dough, and you're watching the cookie cutter come down. Heretofore, or previously, we imagined that every part of the cookie cutter was approaching the dough together, and that this whole bottom of the cookie cutter made contact simultaneously with the dough. Well, if those events are simultaneous in the baker's frame, then they're not going to be simultaneous in the dough's frame. So when I say those events, let me just pick 3 events. First event would be the right corner of the cookie cutter, the right bottom corner hitting the dough. Event 2 would be the midpoint of the bottom of the cookie cutter hitting the dough. And event 3 would be the left corner of the bottom hitting the dough. Those are supposed to happen all at the same time as seen by the baker, but they're not going to be simultaneous in the reference frame of the dough. So what does it look like from the dough's perspective? I've put the arrow up here now to indicate that it's not the dough that's moving. And you know what, I screwed one thing up, didn't I? If this is the baker's frame of reference, then the dough should be length contracted. So I really should have these dotted lines a little closer together. Oops. Okay, but we're back in the dough's frame. You can see that the dough is not length contracted. The cookie cutter would be length contracted, which I don't think I've shown here. But in addition to the length contraction of the cookie cutter, there's another very unexpected effect, and that's that the cookie cutter is tilted. It has to be, because we know from our previous analysis with the space-time diagram and the lines of simultaneity that the event furthest to the right actually happens first. And the event furthest to the left happens last in frame S prime. S prime would be the reference frame of the dough. Do you see the correspondence here between this example and the train? So the high-speed train previously is like the dough now. The dough is moving to the right. So that's frame S prime. Right now we're looking at things from the reference frame of the dough. So not only would the cookie cutter be length contracted, it would also have to be tilted by virtue of moving down towards the dough. And those 3 events that I pointed out were simultaneous in the baker's frame. They are no longer simultaneous in the dough's reference frame. Okay, so now we can explain or resolve the paradox. Imagine event 1 happening first. The cookie cutter first makes contact with the dough. Now, remember that in the dough's frame of reference, the cookie cutter is moving. So while it's subsequently punching out the next part of the cookie, the whole cookie cutter is sliding to the left. So a moment later, it's going to be, see how I made it scoot just a little bit to the left? So by the time the middle of the cookie cutter has made contact with the dough, the whole thing is a little farther over here. And then it moves even further. I'm not exaggerating it a whole lot. See, I'm kind of rolling it out gradually. Let me do that again. Hopefully you can see that this entire cookie cutter seems to be moving to the left while it's punching out the cookie. Not the greatest animation, but it does the job. Okay, so despite the fact that the cookie cutter is length contracted, we still end up with a laterally stretched out cookie. And that resolves the paradox, because when we analyzed it in the baker's frame of reference, we concluded that the cookies would be stretched out laterally, and that's because the dough was length contracted. And when the dough comes to rest and stretches back to its original length, the cookies themselves would also be stretched out. And we can now reach the same conclusion in the dough's frame of reference. And I probably should have made this cookie cutter look a little shorter to indicate that it's length contracted. So despite the fact that the cookie cutter is length contracted, we still get the stretched out cookie. And that's because of the fact that the various points of contact don't happen simultaneously. Truly bizarre, is it not? It's difficult enough to explain this to somebody who has read the chapter on relativity. Okay, what's going on here? All of those points of contact happen simultaneously in the Baker's frame. So if you just pick any two events like left corner and right corner, the time interval between those would have to be 0. And that means when we put ourselves in the frame of the dough, frame S prime, let's look at this bottom equation here. As long as those two events happen in different locations, so the left side of the cookie cutter and the right side of the cookie cutter obviously have a displacement between them. So they may have simultaneously struck the dough in the Baker's frame of reference, and that means that they will not be simultaneous in the dough's frame of reference because delta T prime is not 0. Simultaneous for the Baker, not simultaneous for somebody moving with the dough. Dough! Now, has any real baker in real life ever noticed this effect? Do you think any baker in the history of civilization was punching out cookies on this conveyor belt of dough and noticed that when the dough was brought to rest, the cookies were a little bit more stretched out than they would expect? That's never happened. And that's because the speed of the dough is a very small number. Remember, these cleaned up versions of the Lorentz transformation are only applicable if you're in a system of units where you measure time in meters. And that means that your speed would be a number between 0 and 1. So the speed of that conveyor belt, I don't even know if bakers do it this way, probably not. This is a silly example, but that conveyor belt speed is going to be a number really close to 0. And gamma would be basically 1, right? The gamma for driving a car, even riding in an airplane, even being on the International Space Station is really close to 1. So in other words, this effect is insignificant. So the number 1 times basically 0 times a displacement of what, a couple inches when you're talking about the width of the cookie. So your light speed for the conveyor belt is so close to 0 that the only way to get an appreciable change in the time interval would be, or I should say non-simultaneity. The only way to get a significant non-simultaneity, which causes the cookie to stretch out, as we've seen, would be to have this number or this number be really large to balance out the number that's close to 0, right? Like if the left and right sides of the cookie were thousands of miles apart, maybe there would be a significant difference, or if gamma was really large. So we're going to have to look for a different example if we want the effect to be appreciable. So let's zoom way out from the bakery and consider the Andromeda galaxy, which we know is gravitating toward the Milky Way. We're supposed to be on a collision course, which is kind of terrifying. So I forget how many hundreds of millions of years in the future these two galaxies are supposed to pass right through each other. And yet it's possible that none of the stars will actually touch because there's so much empty space between stars. It's like we just pass right through each other. It's very strange to consider. So I Googled this number, and evidently we are approaching one another at an extraordinarily high rate. Not rate of speed. I don't say rate of speed because it's redundant. Speed is already a rate. So at extraordinarily high speed, 400,000 kilometers per hour. Wow. It seems like we'd be crashing any day now if we're approaching each other that quickly, but there's a heck of a lot of distance between us. Okay, it took me a moment to remember what I had done in this slide. I'm obviously calculating the light speed of our approach to one another. That's the speed of approach compared to the speed of light. This is the speed of light in what system of units? Well, kilometers per hour. It's just a coincidence. When you Google the speed of light in kilometers per hour, it's a little more than 1 billion, billion with a B. So I just rounded it to 1 billion, 400,000 kilometers per hour compared to a billion kilometers per hour is 4 parts per 10,000, 0.0004. Kind of remarkable, right? Even such a high speed, when you express it as a fraction of the speed of light, it's really a small number. And that means our gamma comes out to be, you can try this on your calculator. You don't get any non-zero digits until way out here. And since I only have like 1 sig fig for the speed of approach of these two galaxies, It doesn't make sense to keep all those digits. So gamma rounds really to 1. And that means we just plug in the number 1 here and the number 0.0004 here. And then what about delta x? I forgot to point out what I'm doing here. Imagine 2 events which occur in the Milky Way on opposite sides of the galaxy. And if you didn't know this, we're somewhere here. We're not really in downtown Milky Way. We're not in the boonies. We're somewhere in the suburbs. I think we're something like 50,000 light years. No, I take that back. That would be like 25,000 light years from the center, because the diameter is roughly 100,000 light years. And that number actually depends on how you define the boundary of the Milky Way, because there's this thing called the halo, this spherical region in which other matter is distributed. But let's go with 100,000 light years. Now, previously, we measured distance in meters and time in meters, where 1 meter of time is how long it takes light to travel 1 meter. Let's do something very similar here. And this one you're actually more familiar with. It's a lot like earlier when I said the distance to the sun was 8 minutes, and the distance across the Milky Way is 100,000 years. We really mean 100,000 years if you're traveling at the speed of light. So the speed of light is still the connection. So previously we used a unit of distance, the meter, also as a unit of time. Now we're going to use a unit of time, the year, also as a unit of distance. You can go either way. The connection is always the speed of light. So let's measure distance in years. It's understood those are light years. And we will also measure time in years. See how convenient that is? As long as you stick with 1 unit and use the speed of light as the connection, you're fine. Okay, so we'll plug in a gamma of 1, a speed of 4/10,000ths, and lastly, a distance of 100,000. Remember, it says years, but we're actually talking about a distance here. And what comes out is a time in years. What is that time? Whoa. What is this telling us? If 2 things happen simultaneously on either side of the Milky Way, and I say simultaneous as measured by or observed by somebody in the Milky Way, then they will not be simultaneous for somebody in the Andromeda galaxy. Suppose there are 2 supernovae which explode, or 2 supernovae which occur simultaneously for everybody in the Milky Way. Somebody over here observing, now I say observing, but there's that difficulty with the transit time of the signal. It's going to take a couple million years for the light from the supernova to reach the Andromeda galaxy. So it's not really about when they see the light, it's about when they observed it. So you have to imagine a set of axes attached to the Andromeda galaxy that goes way out here, and the Andromeda people have like a whole bunch of assistants on these axes, and they record the positions and the times of the supernova in that reference frame. They would find that this one actually happened first, and this one happened later. But the time difference is surprising, right? A whole 40 years. Maybe that doesn't seem like a big deal when it takes 2 million years for light to travel from the Milky Way all the way to the Andromeda galaxy. Okay, so even at those kinds of speeds, the approach speed of 2 adjacent galaxies, you're still talking about rather modest changes to time intervals and simultaneity compared to the vast distance between, or the vast travel time between 2 galaxies. But still, 40 years is a lot different than the change in simultaneity for the cookie cutter, right? And that's because we're going considerably faster, 4/10,000ths the speed of light, and we've got a much greater separation between the 2 events. Instead of right corner of the cookie cutter, left corner, which are just a couple inches apart in the baker's frame, we've got 100,000 year span between the 2 events that I'm imagining. That about wraps her up.
Bye-bye. Cookies!